Okay, we are going to hit a full-time hypothesis test. Now, I want you to pull out the rubric that you have about hypothesis testing for means so we can use it and follow what we need to have in each of these parts. Adopted from the Learn by Doing, the federal Pell Grant program gives grants to low-income undergraduate students. According to the National Postsecondary Student Aid Study conducted by the U.S. Department of Education, the average Pell Grant award, average, we like that word, was 2,600. So that's what they said it was in 2,600. We wonder if the mean amount is different. Oh, that's an indicated, that's a word. It's going to tell us what we want in our claim. This year for Pell Grant recipients at San Jose State University. Suppose that we randomly select 50 Pell Grant recipients from San Jose State University. For those 50 students, the mean Pell Grant award is 2450 with a standard deviation of 600. We're going to conduct a full hypothesis test. Well, where do we start? We need to do our state. And in our state, we're going to do a symbolic statement of the null and the alternative hypothesis. The null hypothesis is that the average was 2,600. And the alternative is that it is different. And then we need to make this in words. So the mean Pell Grant award is equal to 2,600, and it's not equal to. In addition, we need to determine our level of significance. Nowhere in this do we see anything about alpha, so we're going to test at alpha equals 0.05 level of significance. And this is because that's our standard level of error that we're willing to allow. We do 95% confidence or a 5% level of error. They kind of go hand in hand. So that's our state. We have identified our mean in context because we've said it in words. We've got our null and our alternative hypothesis, and we've stated our level of significance. Now, when we're doing the plan, we collect the data, we confirm our conditions. So first of all, let's talk about what our conditions are. So in the plan, we're going to, for population means, we're going to calculate the sample mean and standard deviation. They tell us that X bar is equal to 2450, S is equal to 600, N was equal to 50, and now we need to check whether it was random and with independent observations and if our population was normal versus a large sample size. Okay, so conditions here. We're looking for random, and we have it randomly selected. So this is random as stated. And for the normal condition, n is greater than or equal to 30, we can use normal calculations. Moving on to the do portion, this is where we're going to actually calculate the test statistic. Since we don't know our sigma, that means we use our t statistics. So we're going to do a t-test where t is equal to x bar minus mu over s divided by square root of n. And then we're going to get a p-value for that. And we're going to use StatCrunch to get our p-value. But let's recall what our degrees of freedom are. So our degrees of freedom is equal to n minus 1, which is 50 minus 1, or 49. In StatCrunch, I'll show you those calculations in just a minute, we get a t-value of negative 1.768, which is not outside of 2 standard deviations. So our p-value is equal to 0.0833. Our p-value is not low. So we found the p-value in StatCrunch, and we have stated that what's the next thing? We need to state the p-value as a conditional probability about the sample statistic. The p-value is the probability that if 2,600 was the average, then there is 0.0833 probability that our sample would show not 2,600. That our sample would show not 2,600. Okay, in our conclusion, we need to talk about the null and the alternative and link our p-values together. So here we are in conclude. Okay, so since our p-value of 0.0833 is greater than our alpha equals zero point zero 0.01 level of significance, we fail to reject the null. There is insufficient evidence to support the claim. So we've put it in context about the alternative hypothesis, and we've stated that we're talking about the null hypothesis we're failing to reject, and we've also talked about the p-value. So this is our four-step process for testing hypothesis. On the Did I Get This from page 173, suppose we're conducting a t-test for a population mean with the following hypothesis. And we have a sample size of 30 and a test statistic of negative 2.43. What is the corresponding p-value? Well, when we're using this, we need to go into StatCrunch and use the t-distribution calculator to determine what the p-value is. Now, one thing to note is that this is a two-sided test, which means I can reject low or I can reject high. So whatever value we get for one side, we need to double to make it for our two-sided alternative. Going back to problem 4, let's go ahead and calculate the test statistic and the p-value. We go to Stat, and we're doing t-statistics because we do not know the population standard deviation. We use one sample with summary. For our sample mean, we had 26. For our sample mean, we had 2450. Our sample standard deviation was 600. The sample size was 50. And we're talking about a hypothesis test being equal to 2600 and not equal to 2600 for the alternative. And then we click Compute. We had that t-statistic that I said of negative 1.768 and the p-value of 0.0833. For question 5, we want to know how to find the p-value. We need to go to calculators then and use t-calculators. This is like a normal calculator, except you're entering your degrees of freedom. So our degrees of freedom was 49, and we are talking about a not equal to problem, but we're only able to give less than or greater than. And since we have a negative value, we're going to do less than and put in our value of negative 2.43, and we're going to compute. We're given that the direction, we're going to use less than because it's a negative problem, so we're going to enter negative 2.43, and the degrees of freedom that we're going to use is 29 because the sample size was 30. Selecting compute, we get 0.01075997. which we're going to double because we have twice the p-value. Notice that we've got the rejection region on the left. We need that on the right-hand side as well, a mirror image. And so we're going to double that for our p-value. We had 0.011 area here, which we then need to double here to get a p-value of 0.022 for this two-tailed problem. On the Learn by Doing for each of the following histograms, choose the option of how to proceed with the hypothesis test. We're basically checking normal conditions here. If it's random, we're good to go. If the population is normal, we're good to go. Or if the sample size is large, we're good to go. This sample size is skewed, but it's the size of 100, so we can actually use normal calculations for our sample. So conditions are met, it's safe to proceed with a t-test. Here for question 2, it's kind of symmetric. There's not a lot of skewness, but our sample size is only 15, so we're not 100% sure that our conditions are met. So we're just going to say conditions may not be met, but let's just use a disclaimer. Let's go ahead and calculate it and say, hey, it might not be true. And here we've got clear skewness and our sample size is only 17. Conditions are not met. We are not going to use that t-test. It's important that you know, based on your sample size or the shape of your distribution, whether you can go ahead and use normal conditions. Okay, we're going to move on to a matched pairs type situation. This is where we have two things that are related together, like let's say a person takes one type of medicine, then takes another type of medicine, and you're measuring the results of both. It's not like I have two separate populations. So drinking and driving, the Centers for Disease Control and Prevention website cites studies from the National Highway Traffic Safety Administration to support the statement. Alcohol use slows reaction time and impairs judgment and coordination, which are skills needed to drive a car safely. The more alcohol is consumed, the greater the impairment. So all states in the U.S. have adopted a blood alcohol concentration of 0.08 as the legal limit. The CDC website continues that legal limits do not define a level below which it is safe to operate a vehicle or engage in some other activity. Impairment due to alcohol use begins to occur at levels well below the legal limit. It is this last statement that may be surprising to drivers. Interviews with drunk drivers who were involved in accidents reveal that drunk drivers do not realize how drunk they are. I've only had 1 or 2 drinks. I'm okay to drive is a common sentiment. Suppose a college conducts a study to call attention to this issue. Researchers use a random sample of 20 college students to examine the effect of drinking 2 beers on reaction times. They use a driving simulator to measure each student's reaction times before and after drinking 2 beers. The reaction time is the time it takes a student to hit the brakes in a simulator when an obstacle appears in the road, and they're noted below. So it's the same person that you're measuring. You're measuring them before they've been drinking and you measure them after they've been drinking. And so there's that relationship between the two. So they're looking for a common difference for each individual. We have a sample size of 20. And in this situation, we actually have with data because each driver's information is given. Using this information, we want to identify a type 1 error and we want to talk about what the probability of the type 1 error is for this study. Okay, you could go through a matched pairs situation in the problem that on the previous page. You could go through the entire hypothesis testing and check the conditions. I encourage you to run the numbers, put those into StatCrunch and calculate the difference just to kind of see what you get and see what if you match up to what we have. Now, identifying a type 1 error, we need to identify what the null and the alternative hypothesis is then. Now, the average time that it takes to stop based on before you've had drinks and after you've had drinks, we would assume that that's the same. So our null hypothesis is the assumption that the average time is the same for drinking beer versus not beer. And, some people write it as mu D for mu difference, and that's the 1 minus 2 or mu 1 minus mu 2, depending on how you define it. And then we are then going to say that our alternative is that our reaction time is slower, meaning that our before minus our after is less than 0. It's negative because our after is going to be a bigger number. So a type 1 error is when you reject the null, but you shouldn't have. So we rejected that there wasn't a difference when I shouldn't have. So we should say that there isn't a difference in this situation. The researchers conclude that drinking 2 beers slows reaction time, and this is true. No, that's not an error. In reality, drinking 2 beers does not have much impact on the reaction time, but researchers conclude that it does slow. So in reality, this is true, but we're saying this. So we say this, but this is true. That's type 1, which is number 2. Researchers conclude that drinking 2 beers does not significantly slow reaction time, but that's not really true. That would be a type 2. Now, the significance level is 0.05, so alpha equals 0.05. And the p-value is 0.014. Our p-value is low. We would reject. We would say that the average time is slower. What is the probability of a type 1 error? Well, if you remember the chart that I made, I had reject, fail to reject, and then whether it was true or false. So if the null is true versus the null being false, and we reject or we fail to reject, if the null is true and we reject, this is a type 1. If the null is false and we reject, this is correct. If the null is true and we fail to reject, this is correct. And if the null is false and we fail to reject, this is a type 2. And we said that type 1 error is represented using alpha and type 2 error is used beta. So alpha is our probability of committing a type 1 error. So when you're choosing your level of significance, that's how willing you are to allow error to happen. And that's it for this section.